So this is essentially what's happening. If we've got this scenario about g of x, I'm going to establish some interval from a to b here. Okay. So that's my interval from a to b. And between a and b, I've got g of x, which I'm just going to say is some upside down parabola. This is my g of x. Upside down parabola. Now, I also have f of x. And I'm going to let f of x do this. Now, this value right here is going to be my value of c. So, as I approach c on g of x coming in from the left and the right, that would be my limit value, right?
Yes, sir.
And as I approach c coming in from the left and the right, also for f, that's also going to be my limit. So this is both the limit as x approaches c for f and for g. Now, let's say we have some erratic function between the two. And this erratic function between a and b, always between a and b, is between f of x and g of x. And I can't plug in because h of c is probably undefined. It's either undefined or it's really complicated to solve out. Well, I can know that because it's always in between them, that would also have to be the limit as x approaches c for h of x, even though I can't calculate. It's called the squeeze theorem. This is called the squeeze theorem. I have seen it called the sandwich theorem, and I've also seen it called the pinching theorem. But the majority of the time you see this, you'll see it referred to as the squeeze theorem. Are we okay to move on? Now, let's back up. And I know last time we were in class, it was kind of hurried. But we did look at these problems, so let's look at a problem. We're going to put this aside for just a second, and let's say that we need to know the limit as x approaches, let's say, 5 of x over x minus 5. Now, in this scenario right here, we plugged in 5, and this yielded 5 over 0, right? And 5 over 0 was undefined. It still is undefined. That hadn't changed since last time. So the limit as x approaches 5 of x over x minus 5 is undefined. Are we okay with this? All right. Now, we also ran into a scenario, and I know this was not the exact problem that did it, but just for the sake of time, we might have had x squared minus 25 over x minus 5. And in this case right here, if we plug in 5, it yields a 0 over 0 result. And we mentioned that if we come across a limit problem where we end up with 0 over 0, then there is a chance that the limit does exist. And in this case right here, we find this limit by saying, okay, this is x plus 5 times x minus 5 over x minus 5. And the x minus 5's go and play with the dodo bird, so we got 5 plus 5, which is 10. So the limit as x approaches 5 for this one was undefined. The limit as x approached 5 of this one was 10. Both of them are undefined at 5. F of 5 does not exist for either one of these. But this one, do you remember graphically what happened in this case right here? It wasn't a hole. A hole's going to be where we have a limit.
Could that be graphed?
It could be graphed. I don't want us to graph it right now, though. Try to remember. Flip back in your notes if you need to see. Is an asymptote. Yes, we ended up with a vertical asymptote in the case of this problem right here. So, and think about what's happening at that vertical asymptote. At the vertical asymptote, in this case, one side would be growing without bound, the other side would be decreasing without bound. And we looked at that. We looked at that with a magnifying glass. And I think, again, I don't remember if it's this number or not, but we looked at like 4.99 and 5.001, and we got two numbers that were pretty far apart. And then we went to 4.999 and 5.0001, and they were even super further apart. And that's what's happening at an asymptote. They're getting further apart, and they're getting further apart even faster than our minds can comprehend. So, that's what's happening at a vertical asymptote. This one didn't. And we said if we ever end up with a scenario where you have 0 over 0, there is a very, very, very good chance that that limit does exist. Now, again, I'm getting into this. Just be patient with me. Before we do that, though, let's consider the limit as x approaches 0 of the sine of x over x. All right. So, what happens here if we plug in 0? What do we get in the numerator? 0. What do we get in the denominator? 0. So there is a very good chance here, this yields 0 over 0, so there's a very good chance here that the limit does exist. Your only problem is here, well, before I get to this, I do want someone to do this proof for me real quick, that you have the sine of x over n. Yeah, the ends cancel out and you're left with 6. All right, so that's good stuff right there, isn't it? All right, now let's get back to that.
Sorry. It's just a joke, right?
Yeah. It's actually a decent joke. Most of my jokes aren't, but that's a fairly decent one. All right, but what am I saying? You can't cancel these x's out right here. I don't get sin when I have sine of x over x. So there's no factoring I can do here. But there's still a 0 over 0, and that 0 over 0 still says there's probably a limit here. So let's look into how we could possibly figure that out. And we're going to use the squeeze theorem to do this. So I'm going to look at, this is Coach Solis, he's about to teach us in Spanish what this problem is. See?
To slow down. She was speeding through the
It's all good. This is on video. So, anyway, I'm going to try to construct a scenario where I can get the sine of x over x between two values that I do know. And I need those two values that I do know to have a limit as x approaches 0, and that limit to be the same. Now, what I'm not asking you to do here is I'm not asking you to come up with this scenario by yourself. Someone a lot smarter than me knew what to do here. But I want you just to follow what I'm doing real quick, and then after you follow what I'm doing, then you'll see how this works out. So I'm going to go to the unit circle real quick. And on the unit circle here, I'm just going to take the first, the unit circle for positive x values. That's a beautiful circle, or beautiful half circle. Now, in here, I'm going to draw a few triangles. First triangle I'm going to draw is going to be, and yes, there are 3 triangles in one here, but we're going to call this O, and this is going to be C, and this is going to be A, and this is going to be B. So I'm mainly going to be referring to triangle OAB. And I'm going to let this angle right here be my angle X. That is my angle X. Now, from this, how would I calculate the area inside of triangle OAB? What's the formula for the area inside of a triangle? Yeah, it's 1/2 base times height, and which, as you said in this case, is 1/2 of OA times BC, right? Mm-hmm. All right. Now, what do we know about OA? Which is 1 in this case. So my area for triangle OAB on the unit circle would be 1/2 of BC. So just keep that thought for a minute. Now, I'm going to go over here and I'm going to add to this triangle. And I'm going to let this be D. Oh, this is a right triangle, by the way. Both of these are right triangles. Now, how would I figure out the area inside of triangle OAD? All right. Well, I'm going to write an extra step in there. It's 1/2 base times height, right? So it's 1/2 of OA times AD, which does become, as you said, 1/2 AD. Are we okay with that? Now, this area here is less than this area here, correct? Somewhere in between there, I have a sector. So I have triangle OAB, triangle OAD, but the area between there is the area of this sector, and the sector is like a slice of pizza, and I'm hungry. So I'm going to call it sector OAB. So Now, do you remember how to calculate the area of the sector of a circle?
Like it's that over the area of the whole circle over whatever degrees.
Or the area of the whole circle? Yeah, it's a portion of the area of the circle, right?
Mm-hmm.
And you would get that by finding the angle. Let's just talk about that in terms of radian value. It ends up being 1/2 of theta r squared. No, I'm sorry. It's just 1/2 r squared. No, it's not. It's one. I had it right first time. 1/2 theta r squared, or 1/2. Yeah, theta r squared. But for the unit circle here, what is r? 1. So I just get a 1/2 theta here. So, what is theta? Theta is x. So I'm going to call this 1/2 x. Now, if you have a question, that looks kind of weird. If you have a question of why it works, think about it in terms of this. Let's think about a quarter of a circle. What is the area of a quarter of a circle if the radius is 1? Yeah. It'd be pi r squared over 4, right? Which that r is 1. So it's pi over 4. But let's think about what that angle is. What is the angle for a quarter of a circle?
90 degrees.
90 degrees, but in terms of radians, that would be what? Pi over 2. So we could turn this into 1/2 of pi over 2. So this is where we have 1/2 of theta, giving us the measure of that sector. Do y'all see that? Okay. So, let's move on from there. That is the area inside of a circle. Area inside of a sector. So, here is my statement. I know that 1/2 BC is less than 1/2 x, which is less than 1/2 AD. Wait, not AD, AD. Okay. That was lame. But anyway, hoping someone would pay attention to it.
I saw it go through.
Good deal. Now, one other thing to consider here. We're talking about this limit as x approaches 0. So what is happening as x approaches 0? What's happening to the areas of the triangles and the sector? They're getting smaller and smaller and smaller. What will they actually equal to once x hits 0? 0, right? Once x hits 0, they would all have areas of 0, right? But until then, they are all getting closer and closer to 0, and the areas are getting closer and closer and closer to each other. So here is where I'm going to chunk in the or equals. Because actually, if x hit 0, then we would have all of them being equal. Are we still good to keep going? Okay. Now, let's talk about BC real quick. Would you agree here that the sine of x is equal to BC over 1? In other words, remember, it's opposite over hypotenuse, right? So if this is the adjacent and this is the opposite, the hypotenuse would be 1. So the sine of x is equal to BC. Are we okay? Okay, so 1/2 sine of x is less than or equal to 1/2 of x, which is less than or equal to. Now, what about AD? Well, if we talk about AD, this side right here, would you agree that the tangent of x is equal to AD over OA? Now, the tangent of x is also equal to BC over OC, but that doesn't help me any. But it does help me with this larger triangle, because with this larger triangle, I know I have an adjacent of 1. So the tangent of x is equal to AD over 1. So the tangent of x is equal to AD. So this now becomes 1/2 of the tangent of x. So now I'm done with all of this. Now I'm just going to get to the arithmetic involved here. So I'm going to erase what I have over here. And now I'm just to a step, like I said, where I'm thinking about the arithmetic here, and I'm still considering it with the context of the limit as x approaches 0. Okay. So, solving that inequality out, what looks like the next step I would want to do here? Divide by 1/2 or multiply by 2. So, that's beautiful. So I've got limit as x approaches 0 of sine of x being less than or equal to x, which is less than or equal to the tangent of x. All right, the next step may not seem obvious to you, but just understand that as long, remember, x is approaching 0. X is not equal to 0. X is approaching 0. So it's okay for me to divide every term in here by sine of x, because x never actually does equal to 0. So the next thing I'm going to do here is I'm just going to take each term and divide by sine of x. So this now becomes the limit as x approaches 0 of, all right, here's the tough one. What's sine of x divided by sine of x?
1.
1, all right. All right, what is, well, we'll just leave x over sine of x. All right, now, what about tangent of x over sine of x?
Cosine. What? No. It's just
Is it one of the
It's 1 over
reciprocal
cosine.
things?
Well, we can turn tangent x into sine of x over cosine of x, right?
Yes.
So I have this divided by sine of x, which is the same thing as multiplying by 1 over sine of x, right? I took, it's tangent, this is tangent, right?
Yeah.
tangent divided by sine of x is the same thing as sine over cosine times 1 over sine of x. All right,
It's 1 over cosine.
I'm going to leave it as 1 over cosine. Yes, that is secant, but you'll see why I leave it as 1 over cosine. Are we still okay here?
Yes.
All right. So again, we're still talking about the limit as x approaches 0. Now, let's talk about, let's take the reciprocal of each one of these terms. What is the reciprocal of 1?
1.
All right. What is the reciprocal of x over sine of x?
Sine x over x.
Sine of x over x. Uh-oh, does that look familiar to you? That's what we're looking at right here, right? Okay. And what is the reciprocal of 1 over cosine of x?
Cosine.
Cosine of x. Now, when you're doing reciprocals in inequalities, what do you do?
I'll flip the.
You have to flip the inequality around too. So now this becomes greater than or equal to, greater than or equal to. All right, well now let's consider this limit here. I'm gonna, again. All right, so this is, what is the limit as x approaches 0 of 1? Starts with a W. 1. All right. Now, still can't plug in 0 here, can we? But what is the limit as x approaches 0 of the cosine of x?
1.
It's 1. Boom! So the limit as x approaches 0 of sine of x over x is 1. Because we trapped it in between two equations that had the limit as x approaches 0 as 1. I will not